Okay, let's do this problem. A thick spherical conducting shell of inner radius A and outer radius B carries a net charge of plus 2Q. A point charge of plus Q is at the center of the shell. Find an expression for the electric field strength in all three regions. R less than A, between A and B, and then when R is greater than B. So this is going to be a problem about Gauss's law. But before we begin, let's just write down what we know. First, we know that it is a conductor. The shell is a conductor because it says so. What does that immediately tell you? That charges move freely and that the electric field inside the conductor must be zero everywhere inside. So E must be equal to zero everywhere that there's inside the shell, where there's gray here. The last thing we know about conductors is that any charges will reside on the surfaces only. So there will be charge in the inner surface and there will be charge on the outer surface. Okay, and just how much of that charge we will find out. So the first question is, what's the electric field for R less than A? To do this, we can use Gauss's law. To use Gauss's law, we must look at the symmetry of the problem and determine what Gaussian surface to use. It should be clear now that this symmetry is spherical. It doesn't matter which way you look, as long as if you're at the same distance, you will see the same charge. That means you should use a sphere as your Gaussian surface. So if I let this red circle represent my Gaussian surface, I will then put it somewhere inside less than A, centered about the charge, centered around the charge Q. This will be the radius R of the Gaussian surface. Okay, and we write down the Gaussian surface, total flux, Gauss's law, total flux is equal to the total integral of the electric field dot into tiny little surface elements. So this is the total surface area of this red surface, and that must equal to the charge enclosed over epsilon. Okay, now because we chose a circle, the electric field that would be here is also parallel to the area vector dA. Since it's always parallel, there's no more dot product to worry about. And this just becomes the integral of E dA. The charge enclosed is just going to be plus Q over epsilon naught. We're the same distance R away. The spherical symmetry says that the electric field amplitude must be the same, so we can take the E side of the integral like so. Now, the integral of the entire surface will be the surface area of the sphere, which is going to be 4 pi r squared equals plus Q over epsilon naught. Thus, the electric field inside is going to equal Q over 4 pi epsilon naught over r squared. So it will be equal to the Coulomb field. This is just the magnitude. Of course, the direction is in the R. Now, what about number 2, the region inside, in between A and B? So in between A and B, we're going to be inside the conductor. The electric field inside conductor is always 0. So that was very easy. Inside the conductor, the electric field is going to be 0. Now, for the third region, R greater than B, what will be the electric field there? Well, for that, to answer that question, we'll use Gauss's law again. This time, we'll use a Gaussian surface that needs to cover all the charges. So our Gaussian sphere, the sphere has to be has to be bigger than B. Okay, so that's our new Gaussian surface, and its radius still is R. And now the total charge enclosed is going to be plus Q and plus 2Q. So the total charge enclosed is 3Q. If you do the same thing we did before, that the total flux equals integral E dot dA, and the total charge is now plus 3Q instead of just Q. Everything's going to be the same, and so we're going to have E equal to 3Q over 4 pi epsilon r squared, like that. It didn't ask us, but we can also answer the question of how much charge exactly is on these two surfaces. We know that since the electric field is 0, this is plus Q. In order for in here to be 0, it has to enclose 0 charge. So that tells you immediately that the charge inside this inner surface must be minus Q if the electric field is going to be 0. If this is inside the surface, it's going to be minus Q. So what charge is on the outer surface? The inner surface is minus Q, and whatever the charge on the outer surface is, that plus the inner surface must equal the net charge plus 2Q. So if I change this color, say this is the outer surface is Q outer, and Q outer plus Q inner must equal plus 2Q, right? The charge on the inner plus the charge on the outer must equal the net charge of 2Q. Well, that tells you immediately that Q outer must equal, since Q inner is minus Q, then Q outer is going to be plus 3Q. Okay, so that's how much charge is on the inner and outer surfaces and what the electric fields will look like in all three regions.